going on? Today I'm going to be doing some Leet. And for that I'll be working on requests. It's like a front end for curl. Writing the application state. Because to set up parallelism and to also be able to collect like a collection of errors over the programs are running as opposed to just one error per request. It'll be nice to have this like global application state that just allows files being parsed to kind of send their errors up into some higher collection that can then, when all the processes are done running, can be printed out. That was the second most horrible description of something I've ever heard. But you know how it is? Yeah, let's do some Leet first. Group anagrams. Let's do C++ today. Given an array of stirs, group the anagrams together. I like simple problems. How would I do this? Input eat t. These two. These. This is these. Okay. So if I start here, no previous anagrams add. Start here, no previous anagrams add. Start here, no previous anagrams add. Here, add. Here, add. Here, no previous anagrams add. 10 to the 4. 100 characters. So DOM solution. Compare against each. Put this in. If there's no matches, new. If there's a match, put it in. Smarter solution. Just only compare with 1 at each time. I mean, that's still quite trivial, but you could optimize this with some kind of like hashing setup. Imagine like taking the sum of the characters, comparing it. And you could sort them by the sum of the characters. So, let's just write up the compare to each one. That's like n squared is just so shite though. Also, I didn't really check that this is on. Okay. Oh my gosh, I'm on the face screen. RIP. Okay. So let's just consider. So I'm also trying to consider whether it's worth hash table, string, sorting. That kind of sounds like what I was saying. The sums. I'm I'm curious whether it's worth thinking about this or doing twice as many problems. I'm actually going to conjecture that it's more effective to just look at more problems and understand and type the answer than derive the answer myself. Well, let's see. So it looks like he is doing a letter count. Seems similar to what I was saying. Let's look at the frequency count. For each string, computer frequency count. Frequency count as a tuple. As a key in the hash map. Append the original string value to the value list. O of n dot k. There's O of n of k. That's for my first interpretation of that is, but I imagine it's just O of nk. The frequency of each character as the signature. What is meant by signature here? Empty hash map. So that is a hash map of strings to vector of strings. For each string in the array, compute a frequency count for the string. So this is like a 26-bit vector. Okay. Use the frequency count as a tuple. Frequency count converted to a tuple. Now are we seeing how it's a tuple? As a key in the hash map. Then append the original string to the values. So yeah, I think I remember the intuition for this. Let's write it up. So we need this data structure. Okay. This data structure of a map containing, it's mapping a string to a vector of strings. We can call this rec map. Right? And so with this, for every string, how do you write these? So you need this string s in stirs. I feel like there's probably some more characters that need to go in there. Yeah, it's a string reference first off. Okay. So what do we do? So you need a stir builder for C and S. So I could have just done this. For R, C. Not really liking my imported data types. For C, car C, and S. Imagine this can be optimized using a different data structure. E plus. Let's look up C++ build string. Get a stream. Let's do O stream. Key. Yeah. Key C. So it's not key C. Maybe a better way to do this. Maybe a better way to do this is to have a car pointer. Give it a key template. Seek to 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 1 2. How many letters are in the alphabet? 26. Might also be better as a Boolean array. Probably a bool array. How big is a bool? CPP bool array size. Yeah. That is going to be 81 bytes. So is this, so. We'll just let this work. I is less than 26, I plus plus. Nah, that's dumb. That's quite dumb. This is also not Boolean. These are frequencies. Car, C, and S. So index, go in I. No. Uh. This is kind of trash. This is kind of trash. Whatever. We have an index defined as the board of car. You do static cast int. And we're going to do static cast int of C minus A. And so this should probably be an array, yeah. Yeah, it's better as an array because you can just index it better. Standard, or no. How do you make an array in C++, dude? I'm looking for a comparison of C array versus standard array. What's standard vector? C style, simple. Standard array has size, doesn't decay to a pointer, bounds checking, verbose. Let's just go C style. I think I want equals 0 here now. So freak this index plus equals 1. Freak. Then you gotta build freak into a stir. I don't know how that works. That's kind of disgusting. And then you build the output back, right? It's a vector, vectors. So for vector string group in rec map. Can you do that? CPP loop through vec. It's like I need, sorry, loop through unordered map. Pair. It's gonna be first and second. Okay. For auto. Let's auto pair in the map. So we can just do and dot push back pair dot second. Is that a function? No, it's an attribute. Pair brackets or not? Is it this? Int frac 26. Spend declared identifier A. Character A. Set a cast string. Cast int to string. CPP. Or static cast string. Int to string. To string. CPP unordered map. It's a map of string to vec of string. I'm sure I read all that. UMap. Oh my god, shut up. Unordered map. Do I need to include it? Rec map. Key. Why does it not like that? Okay. We're getting it. Rec map key. Why does it not like that? Key is what? Sorry. Key dot stir. So we're missing some cases. Output B D D D D D B C. So did we flip it? It's flipped. So is there ordering? Answer in any order. You can return the answer in any order. B D D D D D D D D D D B D D D D D D D D B B B so B B B B B B B B B C B B B B B B B B B C. Huh? Expected output. So the problem is that they're not in their own arrays. We output that we think they are in the same. Okay, that's odd. They certainly do not have the same. That's quite odd, actually. D. Rack 26. Initialize 0. Static casting the C. Minus A plus equals 1. So, that's quite odd. It's implying because we get the key of the stir. The key is all of the ants and the free. I'm surprised to see that. So let's go to test results. Can I do a custom? Can I do a custom test result here without breaking the UI? Test case, make it big again. Make a new one. Put this in here. Make it small again so I can scroll. Go to description, make it big again. Go to test result, run it. So yeah, I'd like to see out t.stir here. Let's also see out in mine. It's 10. That's funny. Yeah, that's pretty funny. Dang, this is slow. This is slow. Am I using too many data structures? So the one that I was looking at, under map string, vex string, for try making this const. He's using a CBP array. So array int 26. Rec. Color car C. Sure. C minus A plus plus. Oh, you can just do that without a cast. If you look at it as a car. I was making it an int. And then subtracting it. Wait, yeah, that's kind of dumb. That's a little dumb. So let's do freak. C minus A plus plus. That looks better. A string. I imagine this must be better. Perhaps const here. Constant freak. Can just do that character. Key dot start a pushback s. Vector stir int. Const auto freak map. Pushback return. Is this any faster? It's not. Let's use this analyze complexity. Chat Jippity backended. Huh? Интересно. So that wasn't too bad. Hopefully they asked me that one. Let's go to the next. No way, it's still on the screen. Okay. Window. Этого. Next. Conveniently, I've done a lot of these. Does any of these remind me? So, which other ones do I want to do tonight? I'd like to do this one. Or you cache. Find median from data stream. I'd like to do that one. I would do an easy in there. Oh, look at this one. So let's do these 4. What time is it? We're gonna do these 4 with a slightly different tactic. Let me get a timer. Is there a native timer? Yeah, I'll just use the GNU timer. Or the... Probably offended somebody with that. I'll use the GNOME timer. So I'll do 11 minutes on each problem. And if I can't get it, then look at the answer. That'll just give me enough time to fully understand the problem. Compare some tactics. Then I'll look at the solution and write it. Let's do it. All right. One sec.
О, черт. Зач... А? Брат, брат, что? Bro, what the... Oh, hell no. Говорим об этом и... Ебать.
Yeah. Блин. Ха? Зачем нет? Как сделать... Здесь можно. Присесть. Работать. Это тоже. Это тоже. Это тоже. Это тоже. И это тоже. So yeah, now I'm just I had to do some emo, and I'm kind of building my schedule for the next few days. Блин. Ну, я как по-фински говорит. Не... Ну, сису. Да? Брать я уже это... Нет. Хорошо. Я такая, бля. Каждая девушка лучше танцевать. И... Kind of just doing some chores right now, one second. Два часа. 2 часа. Будет... Да... Хм. Третьего? Скажем третьего. Третьего и 40, и 45 будем. Ладно. Alright, so I just built out a schedule for the next 2-ish days. Straight preparing for this interview. Alright. So let me close these. guess I got a lot to do tonight. But that's for the best. Leet. So this is really just going to be Leet tonight. I don't really need to work on request as much as I need to work on my Haskell order book and Gleam and distributed systems. And what was that? And there's only, sadly, there's finite time. So, what I'm gonna do? Chess is right in our cache. So the way I'm gonna do this, we give myself 11 minutes. So how does this work? Wish I could make this bigger. Okay, I give myself 12 minutes. Это лучше. Такая. Alright, I'll do this. So, I'll do this. I'll give myself around 12 minutes. Maybe it should be longer for these like class kind of problems. Let's do a new one. Let's do this one 15. I'll give myself 15 minutes to do this. And if not, I'll look at the answer. And I'll also do laundry in the middle. That'll kind of disrupt my like memorization of the answers. And yeah, I'll look at the answer, but not really too much. Not while I'm programming, I'll say. And yeah, let's do it. So design a data structure that contains a LRU cache. So backed by whatever we desire. So we have a capacity, which is initializes it with positive size capacity. Int get and key. Return the value of the key if the key exists. Otherwise -1. Okay. Put update the value of the key. So ORU cache. Update the value of the key if the key exists. Otherwise add the key value pair to the cache. So the number of keys evict the least recently used key. Functions get and push must each run an O of 1 average. Okay, so we're looking for, just to remind, O of 1 on get. Put. So what am I looking for here? Put should be O of 1. So this sounds hash-ish. And a bit Q-ish without time. How are you? So it has a capacity. Get, return the value of the key. Put, update the value of the key if the key exists. So put, if key exists, update val. Elif free spot, put. Else evict, put. So let's write this first part. If so first we kind of got to know how we're backing this. So how can we know? This is easy. Free spot, we can just maintain like a free list. Else evict and put. So how can we know which one is the oldest? Could have one way to do it. Let's just have a queue. First in with the first out. Always give you the oldest. let's see, I think we have a queue. So you have it hash map backed. So we can just do private here. So you have your standard vector. Sorry, this is a unordered map of int to int. This is called standard queue event queue. You have, are we having a free list? We can have a free list. Standard vector int free list. So when you make this, you want to set So this is quite dynamic, so we actually wouldn't. We can just instantiate. So equals standard. CPP runtime defined array. So let's do a variable sized array for the free list. Free. Int. So we can do free is equal to standard array of ints free is equal to standard array int capacity. Unordered map already exists, and the queue already exists. So let's quickly look at the C++ queue. Queue. Stop. Get away. Queue int equals GQ. How do you make a new queue? You just do that. And you can start pushing to it. Okay, that looks good. All right. So let's do this get. So let's do if of key. Let's look at that up. If so, CBP unordered map. Huh? Unordered map has value. I'm also gonna pause this because I know what to do. That's function hash value. Not hash value, has value. We got no key. What does this return if there's no key? -1. Okay, sweet. Turn our map of key. But if the key exists, update val. So if of key greater than 1, sorry, greater than 0. Can value be negative? Can int be negative? No. Is greater than or equal to 0. So key of what am I doing? Of key is equal to so the hashing function so it's kind of implied that these keys are already hashed, yeah. UMF key, or they're already kind of like, yeah, UMF key is a good value. Return. Just to be here. If there's a free spot. So when you add a key, we're also gonna do free key. So free of key equals false. Opacity true. I'm not sure that's how you do that. We'll see. So if free of key or free of key so if the key exists or it's free, override it, make it not free. Otherwise, you gotta evict the least recently used. This is kind of, I'm not sure if I'm doing this correctly. Because the least recently used. Yeah, I'm not sure I'm doing this right. Well, let's see. So this is the evict case. So how do you evict? Oh, you also gotta put. So used is defined as get as well, right? So we'll do Q. How do you consider the case when you read it a bunch of times? So you like use it a bunch, you have some stuff in the queue. You keep adding to the queue. That is a question. Because you're gonna keep adding to the queue. So you'd have to like remove everything from the queue. Which is kinda AIDS. So whenever you put See, I think I'm satisfied with my understanding of this. I want to see the best tactic for what I'm trying to do with the queue. Let me look at the best C++ solution. So these guys are using doubly linked lists. Interesting. Honestly, that'd be kind of convenient just to watch a video on this. I'll watch this video, understand how to do it, and then start. Shut up.
Questions, and also don't forget to like the video. It supports the channel a
Почему я
lot.
музыку
So this
слышу?
is definitely more of a design problem than an actual algorithms problem. So we have some kind of cache that's going to store values. It has a capacity, so it's fixed size, And we want to be able to get values from this cache based on a key value. If that key value exists, then we'll return the value that it corresponds to. If it doesn't exist, the default value we want to return is -1. And if we're getting values, we also need to be able to put values into the cache. We're putting them in based on key value pairs. And there's a lot of edge cases, and they explain a bit of them to us. If the key already exists in the cache, then we just want to update the value. If it doesn't already exist, then we're inserting it for the first time so we can put that key value pair into the cache. And remember, this does have a fixed size capacity, so if we ever exceed the capacity, then we have to evict the least recently used. So that's why this is called the LRU cache problem. And it also makes sense, right? If there's a key that we're not really using, then that's the one that we're going to take out of the cache. And this is actually pretty similar to how browsers work. So for example, if you're using Chrome and web browsers have caches, if there are values that we're not really using in that cache, then of course we can remove them. Let's also try to solve this the most efficient way, which is each of these operations, get and put, are going to be constant time operations. And it's going to be kind of tricky, but it's definitely possible. So let's just look at the first example. So the input is 2. So that's something that we need to kind of remember, right? The capacity is 2 in this case. And the next operation is put. So we're putting a pair of 1, 1, key 1, value 1. And we're going to keep these kind of in order, right? Because we want to remove the least recently used. So we got to kind of remember in what order are we adding these values in. The next one is another put operation, and we're putting
I understand
2,
the
2.
question.
Of course, for these first 3 operations, we're not really
Okay, I
returning
skipped.
anything, so the output is going to be null. So next we're actually doing a get operation, and we want to get the value that has a key of 1. And remember, we're trying to do this as fast as possible. We're trying to do each operation in constant time. So how can we know instantly what the value is when the key is 1? Well, the easiest way to do that would be with a hash map, right? So we're going to use a hash map to instantly look up the value of every key. We can, of course, do this in constant time, and we know that the size of this hash map doesn't need to exceed our capacity, so we can have only 2 values here, right? So for the key value, we can use the same value that we use for each of our nodes. And for the value, we could also do the same thing. We could use the same value that we use in our nodes, but I'm going to show you why it's going to be a little bit better for us instead to have the value be a pointer to the node itself. And we can do the same thing with the second node that we inserted as well. So for key value 2, we're going to point at this node. So now finally, when we call this get and we ask for the key 1, we're going to return the value 1 that's over here, which is exactly what the output tells us is correct. So since we just used the get operation to get this one, we went to our key, then we found this value, and then we returned that value. That makes this the most recently used value, and this is the least recently used value now. So I'm going to keep track of the most recent and least recent by having a left and right pointers, right? So this left side is going to be the least recently used, and the right over here is going to be the most recent. So therefore, we're basically going to be swapping these 2 nodes, right? And so this portion of the problem is starting to keep the ordering of these. It looks like we're going to need a linked list. And not only a linked list, but a double linked list. Because remember, we can easily look up where these values are, but if we want to also reorder them quickly by for example, every time we use a get operation, we want to take this value and then move it over here because it was the most recent. And so now we're going to reorder the 2 nodes. So now this is the least recently used and this is the most recently used. And since this is a doubly linked list, we need the pointers to be connected. Of course, the hash map won't really need to be updated because these are pointers. They're already going to be pointing to the correct ones, and I'm not going to show that And now we can get to the most interesting operation, the third put. So we're putting a third value, key value, 3, 3. And since 3 is greater than our capacity of 2, then we're going to have to remove the least recently used value, and convenient for us, we know exactly what that value is. So first, we're going to end up updating these pointers to make the least recently used 1, 1 and get rid of this. And of course, we want to replace that 2 since we know it's the least recently used. We want to replace it with the new key 3. And now we also want to update that pointer. We want it to point at the new node. And since the new node 3, 3 is the most recent, we're going to put it over here, 3, 3. And the pointer is going to point here. This pointer is going to point here, and there's going to be a double link between them. So this is basically the main idea. We're going to keep track of a capacity. And before we even operation to get this one over the pointers, we know exactly what that value is. So first we're going to end.
So I'm just curious, how are you accessing? So they call. So you kind of got to make your own like wrapper around this data type.
Updating these pointers to make the least recently used 1, 1 and get rid of this. And of course, we want to replace that 2 since we know it's the least recently used. We want to replace it with the new key 3. And now we also want to update that pointer. We want it to point at the new node. And since the new node 3, 3 is the most recent, we're going to put it over here, 3, 3. And the pointer is going to point here. This pointer is going to point here, and there's going to be a double link between them. So this is basically the main idea. We're going to keep track of a capacity. We're going to have a double linked list. We're going to have a hash map where the key of the hash map is going to be the same key that we get from the input, and the value is going to be a pointer to the nodes. And each node is going to look something like this. And it's going to have 2 pointers, remember? So it's going to have a previous pointer and a next pointer. And don't forget about this right and this left. These are also going to be nodes because we want to have pointers. We want to be able to instantly know what's the least recently used and what's the most recently used. So these are going to be dummy nodes pretty much. So getting into the code, remember we're going to need a node. So before we even write this LRU cache class, let's make another class for that node that we're going to use. And remember, each node is going to have a key value pair. So we're going to get those. We're going to initialize those. And we're also going to have 2 pointers, one for the previous node and one for the next node. And they're both going to initially be set to null. Now, when we actually get into the LRU class, we know that the capacity needs to be stored because we want to know if we ever go over that capacity. We also need a hash map, and I'm going to call that our cache. And remember, this is going to map the key to nodes. And before we even have any values in our cache, we want to have a couple dummy pointers, a couple dummy nodes, which tell us what are the most recent and least recent values that we added. So we can just initialize these to 0 for the default values, so 0, 0. And initially we want these nodes to be connected to each other because if we're putting a new node, we want to put it in the middle between left and right. And we can do that with some pointer stuff. So left.next is going to be right, and right.previous is going to be left. And remember, left is going to help us find the least recently used, and right is going to be most recent. So now let's start with our get function because it's mostly straightforward. If the key exists, so if the key is in our cache, then we can return that value, right? So we can return self.cache of key. Now this tells us the node, remember, because each key is mapped to a node. So to get the value, we can just do .val. And of course, if it doesn't exist, they wanted us to just return -1. Now, the only thing we're forgetting with this get is that every time we get a value, we want to update it to the most recent. So to help us with this part, I'm actually going to write a couple helper functions. So I'm going to write I'm going to write a remove and insert helper function. And these helper functions are going to be applied to our linked list. So we're going to pass in the node that we want to remove from our doubly linked list. And I'm also going to write a function to insert into our linked list. And when we insert, we're going to insert at right. And the remove is just going to remove from the list. So these are basically going to be pointer functions. We're going to be manipulating some pointers from our left, from our right, and doing some stuff. So I'm not even going to worry about that. All I know is that we have a helper function that can remove any node from our list and a helper function that can insert any node at the rightmost position of our linked list. So since we're getting, what we want to do to our list is take this node, self.cache of key, and remove it from our list. And after we remove it, then we want to reinsert it at the rightmost position. So we can just do self. And looking at this, get isn't so bad as long as we fill out these two helper functions for us. So now when we actually look at our put function, let's remember that if we have a key that's already in our cache, that means that a node already exists in our list with that same key value. So before we can insert this new key value pair, we want to remove from our list. So we can get that node by getting our cache and using the key value. So these helper functions are definitely coming in handy for us. So now we can create a new node with this key value pair. So node key value, and we can put that in our hash map. So now our hash map has a pointer to this node, but remember that's not enough. We also have a doubly linked list, so we need to take this node and insert it into our list. So insert and just pass in the node, which is cache of the key value. So the node is stored here and we pass that node into our insert function. Okay, so we just inserted a new value, but remember we have a capacity to worry about. So every time we insert a value, we gotta check, does the length of our cache now exceed the capacity? If it does, this is the part where we're gonna remove and delete or evict the least recently used. So we're going to remove it from the list, the linked list, and delete the LRU from the cache or the hash map. So how do we actually find the node for the LRU? Well, this is why we have our left and right pointers. Remember, the left pointer is all the way at the left, and it's going to tell us what the least recently used was. So left.next is always going to be the least recently used. And so first, we're going to remove it from our linked list by just passing in the node. And we're also going to delete it from our hash map. So self.cache. And we want the key of this node, which is actually stored in the node itself. This is why we didn't only store the value, we also store the key in our node class. So we don't have to return anything in put, but we do now have to fill out these two helper functions, remove and insert. So
I'm not really seeing the
if you have
viewing list thing. Let me just read the editorial in a second. So I'm gonna start doing my laundry real quick. Każda девушка хочет танцевать с тобой. Давай. Где мои наушники? All right. So I got like a 23-minute timer until I gotta get my laundry. Let's finish this problem. What is approach to? Doing it with standard list is kind of dope. Athletic free wave today. Second. This one's actually quite nice. Okay. Here. Not here yet. So. Key at the front of the queue is the least recently used. So yeah, this is what I was trying to do with the queue. Because yeah, you have to remove. Okay, so this replaces the queue. You need a way to store data in an ordered manner such that elements can be removed from any position in constant time. Constant time? Ah, okay, yeah. Because you can just set previous dot next to next and next dot previous to previous, yeah. Okay. Makes sense. Am I on the right screen? Yeah. Yeah, okay, that makes sense. Let's say you have a linked list A, B, C, D. Remove C by doing B dot next equals D. And D dot prev equals B. Yeah. Separation done in constant time. To remove C, before it. We use node instead of a list node. Use node because a list node is already defined. Okay. I mean, I'd probably call it node regardless. Get a key, val, next, prev, and a constructor. As each node represents an element in the data structure, we can also store the key value pair in each node. Let's think about how we can implement the data structure again. We need to achieve the following functionality. Store, update, -1, yeah, I recall this. So. Updating and adding involve adding a key to the most recently used or the back of the linked list. So you need a reference to the tail. Into the head as well. True that we can remove a node from a doubly linked list at any given position and node, but only if you already have a reference to the node. Given a key, how can we find the node associated to it without? In our hash map, instead of mapping each key to its value, have it map each key to its associated node. Nice. Now on task 5, when we update or fetch a key, we can reference the hash map to find the key's node in our form. Task 5, what is task 5? Updating. Updating the linked list. So, when we update or fetch a key, we can reference the hash map to find the key's node in O1. Correct. Once we have the node, we can remove it from the list in O1. And you can add it to the tail in O1. Oh, it's not. How do we get? We just use the first hash map, node.val. It's like an edge case. Maybe we're going to need to remove from the front of the linked list and add to the end of the linked list. So there's an annoying edge case if you got to remove from the front. This is empty and we call put. Create a node for this key value pair. Set it as both the head and the tail. Capacity is 1 and we call put again. Sentinel nodes. It be set to dummy node. Okay. So yeah. With that said, let's try to implement this.
So, in the private scope. Yeah, bye.
Scheiße.
Ебать. Я просто срал в танах. Пиздец. Ладно. We're gonna have a standard.
Scheiße. Okay.
Alright. Privates. What do we have in here?
So let's have a new class, yeah. It can just be a struct. It can just be a struct. Struct, node. Yeah, you kind of want to be able to create them easily. Let's call it a class. No. Public. Or I can just make it protected, right? So we'll have a key int val, the node next, node reference next, node reave, and we'll have a node function int key int val, node pointer next, node pointer reave. It'll be key 0. Sorry, key val next start with no pointer. Reave, no pointer. Wait, you can make a constructor on a... Okay, so yeah, you don't start with these. You can put a constructor on a struct? I did not know that. Okay, so yeah, my syntax is off here. So with that, we have nodes. So what do we start with? So you want your sentinel nodes. So we're gonna have a head. Gonna have a node, head, node, tail. I have an unordered map int to node un. Yeah. So to start, I'm gonna make a new node 0 0 head goes node 0 0 tail. Let's go to the address of that. Node 0 0, yeah. And equals unordered map int node capacity. So is that real? How do you make a pointer in C++? Am I slow? Am I slow right now? Editorial. Node, here we go. So previous instance takes in. So I'm really just trying to skip, not look at too much, and just look at what they have in the class. don't want the capacity. Node pointer. Head. Yeah, that's smarter just to do them here. New keyword node -1. I agree with that. New pointer node -1 -1. Yeah. This capacity. Let's go to capacity. And it's not even actually doing anything with that. Just going head, next equals tail, tail, rev equals tail. Okay. So, what do you do when you're trying to get something? So when you get something, return val if exists, or -1 if not. And then you got to update ORU. So when do you update the ORU? You update the ORU if capacity met well, you update the ORU either way. Yeah. So you use the for this. So if so I think either way you can just forward the value of key. But then you got to update we recently used. So the way you do this is we can call remove key, call remove of key, append of key, list remove, you can call it list append. Let's call it ORU remove. So you remove it, you append it. I guess that's only if there's a value though. So if key is greater than or equal to 0, you do this. Otherwise, you return -1. Void ORU remove. Taking in a node. Then we're going to have void ORU. Pad. Taking in a node. Yeah. So in this case, you do what? You do node dot brief, or this is a pointer node. Node next. Sorry. Node prev next. Prev next. You get a node next. Wait, okay. What do you need to do? You need to take the previous and make it next previous. Or what's it? You need previous next. It's going to be equal to next. And you do node next prev. It's going to node prev. Del Leet. Do you need to free the node? How to free a node C++. You just call free. Delete. Delete node. How are you append? So you're gonna do tail. Tail. Hmm. Tail prev. So this is the actual tail. Tail prev. So this is the current last node. Tail prev next. This is good on that. Tail prev. This is good on that. Right. So I accidentally kind of cheated on. Like I didn't see this, but I came to the same conclusion. Get so. Yeah, it's gonna be val. So let's adopt their function. If find key equals, it'll return to end. Huh. In this case, you'll return negative. So in this case, yeah, so you got to get the node. So you can just do node equals key. Okay. So when you put, what do you do when you put? You. How much time I got? I got 48 seconds. So I'm gonna go ahead and head down to my lunch. Still gotta clean my sheets. There's only 6 out of 20 washers working, which is kind of embarrassing. Put. What are we doing in the put case? So, if capacity free, so in the knife case, how do we know when the capacity is free? How do you know when the capacity? Is there like a LAN of the map? dot size is less than capacity. So I need to make a new node. In any case, yeah. So make a new node. We're making a key and a value. Key is equal to node. So else. So either way, we're gonna have to edit the list, yeah. So we can go ahead and do this. So this involves eviction. Here we are updating the list. So it's just a separate room. This involves appending, yeah. Now are you append node? Is that it? When you're putting, you could also be overriding. You need to remove, so first off, it won't be the node that's there, it'll be the key. Or the inverse of what I just said. So I think that might actually just be enough. So in this case, you remove the fed. Yeah. So you LRU, remove head. Maybe this should return something. Oh, you remove head. Next. So what do you return? Well, let's just evaluate our stuff. So it looks like I vastly oversimplified. Constructor capacity get, find, and remove and add. So in the put case, the add case, so they kind of did a bit too much here. Do you need to do this when you add a node? And aren't you just adding it to the end? Tail prev. Next is node. You update your node to do node as well. See, I missed doing node as well. Then you do node prev is equal to
tail. So you gotta do this before you do tail prep. Node. So you know node next is gonna equal tail, yeah. But then you gotta set tail. Sorry, we're doing node prev is equal to what? It's equal to the tail prev. Yeah, okay. Remove. It's not deleting the node, but I think that might be implied when both of its pointers are null. Where there's nothing pointing to it, that might even be implied. So in the put case, what am I missing here? If the key is in the thing, this is the safe headphones pauser. Okay. If the key exists in the dictionary, what does that mean? The key is just the, I think the thing with this is that you're not replacing, it's kind of confusing because you're not replacing the least recently used one like you would. It's not actually hashing the int. Like you're not replacing the one with the same hash as the int. You're just maintaining the capacity. Yeah. So that was a bit confusing in the beginning. Dict.find key. So what are we doing in this? If dict.find, sorry, um.find key. Moving dig of key. Oh my god, I keep saying dig. Of key. So if it's there, you gotta remove it. Yes, I agree. Clear LRU of the old. New node, miss. And then we consider this an access, so that's what I was doing here. Of keys node, LRU of pin node. So I was actually closer than it looked. The only thing I missed was just um.arrays. Node key. If we're above the capacity, erase the key. Wait, if we're above the capacity. Oh. This is the previous, yeah, so you gotta remove the first one. Or you remove, and that also involves All right, let's do it one more time from scratch. Or you cache. So what do we need here? We need a node. This will have a int key, an int val, a node pointer, breathe, and a node pointer next. We can make a constructor here. So it's a node of int key and an int val. Key, set this to key. Have a val, set this to val. Have a prev, can just be a null pointer. Next can be a null pointer. And what do we have in this ORU cache? So we'll have a head. Store the capacity as well. Have a head. Have a tail. What else do we need? We need the map, so we can have a unordered map of head. Sorry, what am I doing right now? This map's what? This map's keys to nodes. Node pointers. This UM. Yeah, that's all we need. So when we make this, we can actually go ahead and inline the head as being a node. Just -1 and -1. Node. Node with -1, -1. In this cache, we'll have, so we'll set our capacity this. Capacity. Head, you also just need to do head next, this is a tail. Tail, rev is a head. So, whenever you get a key, what do? So, there's going to be the case where it exists and it doesn't. So if um.find, if it doesn't exist, which would be um.find key is equal to um.end, then we just return it. Otherwise it exists. So eventually we're going to be returning of key val. What do we do before that? We update the ORU. So we do ORU remove key, of key. So we can actually say, we can just kind of inline this a bit better. Actually, no, we won't. It'll be optimized. Maybe. ORU append of key. And then return the val. So let's write these functions here. So these are going to be void ORU remove node pointer node. And we'll also have a void ORU append node pointer node. So what do we do in the remove case? You get the node, so you do node. You're going to set the previous next to node next. You're going to set the node next previous to node previous, yeah? In the append case, you're adding it to the back. So adding it to the back involves tail prev next equals node. Then you do, so you got to set the tail prev, so tail prev. Node next is going to tail. And here we're going to have to do node prev is going to tail prev. Right? So into put. What do we do in put? So some things I know, if capacity exceeded, evict. And at the very basic level, we need to make a new node. So node is equal to a new node key value. We're going to need to, so if key exists, overwrite. The overwrite will happen implicitly just by doing the same thing as adding it. So we need to clear the ORU. So if key dot or I guess it's like like find key doesn't equal dot end. What do you do in this case? You clear the RU. So you do RU remove key. And you also got to remove it from the dict. So we'll do dot erase key. So we'll also write this logic for, so let's do this first. You make a new node, of key equals node. ORU and node. That's the easy part. Now, if capacity exceeded a bit. So capacity exceeded is the case. What denotes the capacity being exceeded? This is when the that size, is greater than the capacity. So what do? You ORU remove head next. And you do dot erase. So actually, I don't think you even need to erase the key because it'll just get overwritten. But you do need to erase head. I guess before you remove it, you should probably do head next key. So we got an error here. Expected something. Oh, yeah. Expected this. Yeah. Yeah. Pref. Reprieve. Nice. Next. Let's do the easy first. Who doesn't want something easy? Reverse bits of a given 32 bits unsigned integer. What's the best way to do this? Reverse the bits. I don't know. I'm not seeing any like mathematical thing here.
Why are we doing this? Reverse the bits. Because it's not just inverted. It is literally reversing. I'm just gonna look at this. This is actually a good question. Hmm. How does n% to, oh, okay. Where the OR operation? You're starting at the 31st power of 2. Ret plus equals n and 1. The rightmost bit. The left shifted to the power. Let me see what the limited amount of reading I did on that. If I can do this. So ret. So 32. T ret. Power. While n is greater than 0. So what do we need to do here? Get the leftmost bit of n. Make it the rightmost bit of red. Alright, let's do get rightmost bit of n. Make it the leftmost bit of red. So, get the rightmost bit of n. This is n and 1. What data type are you using for this? Ret plus equals n and 1. Okay. Yeah, so ret, okay, ret plus equals the rightmost bit of n to the power. So that's doing both of these. But to ensure that it continues to be the rightmost bit, so you got power plus minus. And then you want to do n right shift. Why is this not working? Ret power n equals 0. N and 1. And oh yeah, I'm not actually updating it. Okay. 7 megabytes? Somewhat surprising. So, what's the more efficient way? Byte by byte with memoization. Someone might argument it might. So this is just having a mapping of every byte to its reverse. Yeah. So I guess that is useful for doing this a ton of times. So, I mean, yeah, nobody's going to know this. No way they're expecting, yeah, okay. That's kind of crazy. Dang, this is wild. That's kind of cool. That's kind of dope. I don't really understand the point of showing this. Like, there's no way I'm gonna actually know what that is. This is going by byte. Huh? Why would you put this in here, dude? Alright, I'm just gonna be satisfied with this. This question's kind of dumb. Yeah, I mean, this like what is this, dude? The expectation to just use this is kind of low. So, two hards. So, let's try to be efficient here. We got 13 minutes. That's how I need to get to my. So, this is better used. Ooh, have I had this on the whole time? I just had that on the whole time. So, I mean, I guess I'm leaving it on because I'm about to do some more stuff. So, I'm about to look at IP. I'm gonna go to the bathroom and do some other junk. I'm gonna go to the bathroom, update my website. Okay. What's I just put it on the bathroom screen, right? Just go to this or something. Alright. I'm still like in the middle of doing stuff, but I can eat a bit. Kind of spent a lot of the last hour just dead. Let's just look up a Leet code. Let's just look up video because I'm gonna eat something and then eat dinner. Leet code 295. Is there a solution? Oh, sweet.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve find median from a data stream. So this is another hard problem, but it's not super difficult if you know the data structure behind it. So they basically tell us we know the median is defined as the middle value in a sorted integer list. If the list is even, there is no middle value, so you take the average of the two middle values, right? So with this sorted array, the middle value is 3, so the median is 3. With this, there is no middle value, so you take the two middle values, add them together, divide by 2, and then you get a median of 2.5. And so we're actually designing a data structure that's going to have two operations. One operation is going to be adding a number to our data stream. So we actually have to store the list of numbers, and that list of numbers is not constant. It's going to be changing every time add number is called. And then from that list of numbers that we're going to be maintaining ourselves, we are going to need to constantly be finding the median of that list. So every time this function find median is called, we have to return what the median is from the elements so far. So this is just an example. If we add num1, then our list is going to have 1 in it. If we add another number 2, then our list is going to have 2 numbers. Then if we want to find the median, we will take the average of these two, and it's going to be 1.5. After that, we'll add another number 3, and then we'll find the median again. In this case, the median is different because our list got updated. The middle value is now 2. So what's the most obvious way to solve this problem? Well, I basically just hinted at it, right? So the obvious way to solve this is insert elements in order. So let's say these are the function calls that are going to be made. So we're going to add 4 numbers, and then we're going to try to get the median. So we're going to maintain a list or an array, right? And every time we get a function call add 3, we're going to insert in order just like it says up here. And basically, if our array is always sorted, then it's going to be easy to identify the middle number, right? Which is going to be the median, right? So the median is always going to be in the middle position. And if our array is sorted, we'll always know where that is. So the first one we have is add 3. So just add it to the first spot. Next, we want to add 2. So how do we do that in order? Well, we have to traverse our array so far. So we see that there's a 3 over here, right? So then we got to replace that 3. We shift the 3 to the next position, and then we put a 2 in the position that the 3 was initially at, right? So now our array is in sorted order. We had to shift some elements, and we had to search for the spot that we put the 2 in, right? So you can tell that every time we add a number, it's going to be an O of n operation, where n is the number of elements we have added so far. So we added 2. Next, let's add 1. Well, we're going to traverse the array, right? We're going to see, okay, the first element is 2. We know that 1 is less than 2. So really what we're going to do is cross out the 2, cross out the 3, right? Shift the 2 over here, shift the 3 over here, and then put a 1 here. But I'll just, to keep the picture simple, I'm just going to put the 1 over here. But we know that in the worst case, every time we insert an element, it's going to be O of n. Lastly, we're going to take the 4 and add the 4. So we're going to see operation up structure. So I'm going to have 2 heaps in this case, a small heap and a, but I'm not just going to have arrays. I'm going to use a heap or a priority queue. So we're going to use a heap.
He's going to use a heap backed priority queue. Alright, let's continue.
Heap data structure. So I'm going to have two heaps in this case, a small heap and a large heap. Small heap, all elements in the small heap are always going to be less than or equal to all elements in the large heap. Also, the size of these heaps is always going to be approximately equal. So if there were two elements in this heap, then there has to be two elements in this heap. What if we had an odd number of elements? So what if there were 3 elements in this heap? That's allowed because we know that we can't actually have these be equal if there's a 2 and a 3, right? Or in the opposite case, there could be 2 elements here and there could actually be 3 elements here. That's also allowed because we know that's approximately equal. If the difference though is ever greater than 1, so if there were 4 here and 2 here, we know then we'd have to balance them, right? Make this equal 3 and make this equal 3, right? We always have to keep it as balanced as possible. And if you're not familiar with what exactly a heap is, it's basically like a list. It's pretty similar to a list. It's implemented using arrays or lists. The only difference is, though, adding a number, we don't add at the beginning or at the end. We just add elements to the heap, and adding an element to this heap is always going to be a log n operation. And removing an element is also going to be a log n operation, right? So add or remove
I thought the
is
heap was
log
going to be
n. And
maybe
there
he's
happen to
using
be
a
2 kinds of heaps, a
list,
max
a
heap
vector-based
or a
heap.
min heap.
Or sorry, a
And
vector-based
the
p
thing
cube.
about these is, so for
But
a max heap,
I imagine the heap would be
finding the
true-based.
max in this list, so find max in a
That could
max
also be
heap is
super dumb and
always going to be
weird.
O of 1. So that's the advantage. We know that finding the max in a regular list is O of n because you have to search the entire list, but with a heap, we can find the max in constant time. Similarly, with a min heap, if you want to find the min, that's also an O of 1 operation. So with that being said, the small heap is going to be implemented as a max heap. And the reason we have a max heap and not a min heap, it's kind of counterintuitive, right? If this is the small heap, why are we using a max heap? And for this one, we're actually going to have a min heap instead of a max heap. And the reason is, what if we had elements to these heaps such as, right? What if we had these elements in each of the heaps, right? We see that all elements here are less than or equal to the elements in the right heap. But if you actually want to find the median of these, we know we need to get the max value in the small heap, right, 2, and we need to get the min value in the large heap, 3, add them together, and then divide by 2, right? That's how we're going to get the median. So that's why we need the min heap, right? We always want the minimum value from our large heap, and we always want the max value from our small heap. And of course, finding the median like this way, right, getting the value from each of the heaps, it only works if the size of the heaps is approximately the same, right? If in this case they're equal. But what if we had a third element in this heap? What if we had a 3? Well, they're approximately equal, right? But you can see the length of this one is greater, right? But the difference in length is 1, so they're approximately equal. In that case, how are we going to find the median? Well, since we know that the length of this heap is bigger than the length of this heap, we know that we have an odd number of elements in that case, right? If one heap is bigger than the other, there's always going to be an odd number. And in that case, we're going to want to get the value from this heap. So if the length of this heap is bigger, we're going to want to get the max from here. We're going to want to get the max value from this heap, and that's going to be 3. And we know in this case, 3 happens to be the median, right? Because look at them, these values are in sorted order. We get rid of these 2, we get rid of these 2, the middle value is 3. And I'm not going to walk you through this case, but let's just say, imagine we had a 2 over here. The exact same thing would happen, right? We would get the min value from here, we get the 2. And notice that, look, the max value from here and the min value from here are equal, right? That's why I say every value in here has to be less than or equal. It's possible that they are equal. Okay, so now let me just go through a quick walkthrough of this code again. So what we're gonna do, add the first element, which is a 3. Which heap are we gonna add it to? In this case, it doesn't really matter. So what I'm gonna do is just by default, add it to the small heap. So let's add 3 to the small heap. And we know that that was roughly a log n operation, right? Next, let's add 2. So by default, I'm always going to take whatever element we add and I'm going to take it and add it to the small heap. Now I added 2 to the small heap. But wait a minute, now the heaps are not approximately equal. This has a length of 2, this has a length of 0. It was okay when this had a length of 1 because that's still approximately equal, but 2 that's too big of a difference. So now what we're going to do is find the length of this one is greater, right? But the difference in length is 1. And now if we get the maximum from here, big of a difference. So now what we're going to do is find the max value in this heap and add it to this heap, the large heap, which is always going to have elements greater. So we know the median list, and I'll show you the heaps, large and small.
So yeah, I guess you have these two heaps, min and large, or sorry, small and large. Small is a max heap, large is a min heap. You add elements to, so you have the median, you add elements based on the median. And if the difference between the sizes, excuse me, is 2 or larger, then you move the elements like down the gradient until it's not.
Large is going to be a min heap, small is going to be a max heap, and the heaps should be roughly equal to roughly the same size. So in Python, you can actually have a heap be just a list. And I'll show you the other things we'll need to do later. So actually in Python, since these are members of this object, large and small, we need to have self as the prefix. And so now we have 2 functions to implement.
Wait.
Find median and add
You
num.
don't have to
Start with
explicitly
add num.
declare the
so
numbers.
just
You
like
can
I
just
showed you, what I'm
implicitly
going to
have them
do is I'm
That's
always
actually
going to
so
take
AIDS.
num and add it to the small heap. So heapq.heap push. This is how you do it in Python. Other languages might be different, obviously. So to the small heap, we're going to push num. Now, Python is kind of annoying in that it only implements min heaps. We know small is actually a max heap. So to get around that, what I'm going to have to do is take every number and actually multiply it by -1.
That's
This
so
allows
AIDS.
us to actually implement a max heap, which isn't implemented by default in Python for some reason. But what I'm doing here is taking num and adding it to the small heap, the max heap, right? But now we want to make sure every element in small is less than or equal to every element in large, right? So every element in the small heap has to be less than or equal to every element in the large heap. So I'm going to make sure that that's true. So if small and large are non-null, and so from our small heap, our max heap, what I'm going to do is get the max value from it. So how can I do that? I can just take the index of 0 because it's implemented as a list. Heaps are implemented as lists. So if you get the 0th index, you're getting the max value. We know that every time we add a value to the small heap, we're multiplying it by -1. So to
I guess it is
reverse
a
that,
list.
I'm going to take this value and multiply it by -1 and get the true.
Okay, I'm done. That's my B. My B.
True value that we actually added to the heap. And so I want to know, is this value somehow greater than the smallest value in our large heap? How can I get the smallest value in our large heap? I can do the exact same thing, index of 0, but I didn't have to multiply this by -1 because this is a min heap, and that's what Python does by default. So if this condition is true, let me make it look a little nicer. So that mainly this condition is true, meaning that some value in our small heap is greater than our large heap, then we have to pop from our small heap and then add to our large heap. So I'm going to heapq.heap pop. So I'm going to pop from our small heap. I'm going to get the largest value from our small heap, store it in val, and then I'm going to push that value to our large heap. So to our large heap, I'm going to push that value. Basically exactly what I did in the picture, but maybe the code is a little confusing. Oh, and actually, since we know every value pushed to the small heap is being multiplied by -1, to reverse that, we have to also multiply by -1 when we pop from it. because look, when we push to it, we multiplied that number by -1, but to our large heap, we can actually give the correct values. We don't have to multiply by -1. That is actually probably one of the more confusing parts about this, which is annoying because there's no way to really get around it in Python. So now we checked this condition. The only other condition that we have to check is what if the size is uneven? And so by uneven size, we actually mean a difference greater than 1. So if the length of small is greater than the length of large plus 1, that means the difference is 2 or greater. In that case, what are we going to do? This is too big, so what we're going to do is pop from the small and then push to the large, which is actually exactly what we did up here. So I'm just going to copy and paste that. And the other case is if the length of the large heap is greater than the length of the small heap plus 1, meaning the difference is 2 or greater. And in that case, I'm basically going to do the opposite of what we just did up here. So let me copy and paste that. So we don't need this -1 because we are going to be popping from the large heap, which has the correct values, not the -1 multiplied values. And with that value, though, I'm going to take that value and add it to the small heap. And actually, we are going to need to take this value and then multiply it by -1 because we have to do that whenever we add to this small heap. So now we are making sure we take every element, add it to one of the heaps, and if there happens to be a size difference, we are handling that. If there happens to be an order difference, right, like the values are in the wrong order, we're handling that as well. And remember, all of these heap operations are log n operations, log n. And now the last thing we have to handle is finding the median. So one case is that there's an odd length. How do we know if there's an odd length? Well, if the length of small was ever greater than the length of large, we know that then we have an odd length, right? Because maybe one of them has 3 elements, the other has 2 elements. We know with this function, we're always making sure that they're about roughly equal. So if this evaluated true, that means we have an odd number of elements, and small happens to have an extra element. So what we can do is return the largest value in small, which is stored in index 0 of small. If the opposite is true, if the length of large is somehow greater than the length of small, we know that the opposite happens to be true, so we can return the smallest value in large. Now, if neither of these evaluates, that means we have an even number of elements, so each of these heaps has the exact same size. So what we can do in that case is return the largest value in the small heap plus the smallest value in the large heap, add them together, and then divide by 2, and then return the result of that. So here is the final code. It's 34 lines, but you can see we have some comments and some, boilerplate type code, but the code itself that we had to write was relatively short, right? Because we did this with a heap and we did it pretty efficiently. Let me just run it to prove that it works. Okay, just one time I forgot to say that this small is a member object, so self.small. And I actually forgot to do that in a couple places, so let me just fix that. So self.small, self.large, self.small, self.large, self.small, self.large, and a couple more places. Okay, so we corrected the self errors. One last thing I forgot is, remember, small has negative. We multiplied the numbers by negative, so when we're getting the number and actually trying to calculate the median, we have to take that number and multiply it by -1 before we add it to this number and then divide by 2. And let me not forget to do the exact same calculation when we're returning the value here, right? So I somehow had too many bugs in here, but okay, so now finally, this should be the final code. The big thing in Python, at least, is to remember these -1s. If you're doing this in C++ or Java, I'm pretty sure you will not have to worry about that. This should be the final code finally, and you can see, yes, it is pretty efficient. And in Python, at least, it's not a lot of code. I think even in Java and C++, it shouldn't be that much code either. So I hope this was helpful. If you enjoyed, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon.
Crazy. Doing it in like 2 bylines is crazy. Lib standard C++. Dang, it's late, bruh. Statistic trees. There's so many ways to solve this. Oh my god. Reservoir sampling. Segment trees. A lot of insertions or a lot of read queries. Limited range of input values. Introductory. Yeah, I mean, I'm good. I'm satisfied with the 2 heaps. But I gotta go get my laundry. This already looks a lot cleaner than what Nico did. If load.size is bigger than high.size, return load.top. Else average. So maintain the size by only ever having the bigger one in law. If high.size is lower, put it on. Alright. So you need a priority queue. Int low. Priority queue. Why does it have a vector? CPP min heap. Why is it a vector? What is that? Or you can do the -1 crib. I'd rather just do this, even though I don't understand why it has a vector there. So we'll have greater event here. High. So the constructor so I imagine that there's not really much to construct. Disagrees, there's no constructor. Okay. So what do you do when you add a num? So what do? By default, you just add to low. Balance. So let's go ahead and do this. So load up push num. So balance involves doing. Let's try not to look at that. Balance involves doing what? Low high dot push low dot pop high dot pop. Do you do this conditionally? Let me turn this off. So low push, high push, low pop balance. Then we have if low size. So let's look at this. If low dot size greater than high dot size. So is this possible? Imagine it would actually be this. And what do we do in this case? I'd imagine we do high dot. We do low dot push. High dot top. High dot pop. Yeah. I've also been acting like this is. And then find median. So if low dot size. So low dot size can only ever be greater. So if low dot size is greater than high dot size. Also just revised that. Is that up? So if low dot size is greater than high dot size. Then return low dot top. Otherwise, you're returning the average of load.top plus high.top slash 2. No, this is rounding incorrectly. No. Off by 1. 1, 2, so nothing. Let's see what. Once it does a double. It's kind of annoying. Still incorrect. That says it's better return load on top. Otherwise, you have this top of the load on top. Let's hide on top. Times 0.5. Huh? What am I missing? Integrator high. Until load up push not balance. If load size is less than load up push, head up top, find median. If the load size is greater, return down to 0. Otherwise, double load up top, let's head up top. 0.5. Huh? What's the difference, bruh? Huh? What am I missing, dude? Load on top plus height on top times 0.5. Cast it to a double. That's identical. Load up push. High dot push, load on top. Load on top. Load up. Oh, I'm dumb. I'm so dumb. Okay, I missed. Alright, so the last thing I'm doing, resetting this from the top. So we're not going to do constructor because we're going to do a 2 heaps balance. So you can imagine as we add nums, we have a min heap. We have a max heap that holds the lowest half, a min heap that holds the highest half. We'll either be in a state where they're both the same size, or the left one has more, and we can maintain that in the add function. So as we get in more numbers, we'll by default add to the lower heap. Then we will add the number in the lowest heap to the highest heap. And if there's more elements in the higher heap, we'll add them back to the lower heap. It's kind of dumb for the lower, like for the first few elements. But it maintains a nice property so that when we want to find the median, we don't have to see if one is larger than the other. So already just to find the median, we'll have 2 cases. One of them is the left has one more case. The other one is the equal case. So in the equal case, we just return the midpoint of them. So we're going to cast a double to, I guess first use some data types, right? So let's make a priority queue. Int called, actually high. By default, it's going to be a max heap. Low will be the max heap. And then to make a min heap priority queue int vector int and a greater function. Ooh, sorry, this is high here. And so we'll return double of low dot top plus high dot top times 0.5. Just to calculate the 0.5 on the right side of that. Go to this. And so in this case, if West has one more, and we can just generalize that as flow dot size is greater than high dot size. If that is the case, return low dot. Otherwise, return that. So now, when you add stuff, by default, we can just add it to so low.push num. Then we're gonna balance them. And you'll do this by doing high.push, low.top, low.pop. And then we will maintain size eq or left bigger. And to do that, if low dot size is less than high dot size, we don't want to just forever push items to that one. Dude, where is my bracket, dude? Oh my gosh, I need keybinds in here. So if this is the case, we'll do the inverse of what we just did, which is low.push high.top, so we're just like transferring it back over. High.top, yeah. Semicolon. Semicolon. Size is a method. Rip. That's that. So I'll save this one for tomorrow. Isn't there like a wish list? Save to do. I actually want to go to this to-do list. To do. I think I know these. We can do this one as well, but the priority is here. Alright, so I'm gonna end it, take a shower and go to bed. Be back on hopefully around 7.